In this chapter, we're going to explore a couple of revolutionary technologies that have totally changed how we find and generate information. We're talking about semantic search and retrieval-augmented generation, or as you'll often hear it called, RAG. These two are basically the reason why search has gone from this rigid, keyword-based thing to a much more fluid conversational experience. So let's dive in and unpack how this huge shift actually happened. You've probably noticed this, right? For years, searching for something felt like a game of guessing the exact right keywords. You had to think like the computer. But now, you can just ask a question, in plain English, and the search engine just gets it. It understands your intent. Well, this isn't magic. It's a fundamental shift in the underlying technology. And today, we're going to pull back the curtain and see exactly how it works. So the first big idea we need to wrap our heads around is the difference between keyword search and semantic search. Keyword search is the old way. It's super rigid, super literal. It looks for the exact words you typed. If a web page doesn't have the phrase science precision, it's probably not going to show up. But semantic search, it's all about being flexible and contextual. It's designed to understand the meaning behind your words. So when you ask, how precise was the science, it gets that what you're really asking about is scientific accuracy, even if those exact words aren't there. All right, here's our game plan for making sense of this semantic revolution. We're going to start with a quick overview of the core techniques. Then, we'll get into the real engine of semantic search, dense retrieval. After that, we'll look at how re-ranking can make those results even better. Then we'll move on to RAG, which is where search meets generation to create some really solid fact-based answers. And finally, we have to talk about a super important question. How do we even know if these complex systems are any good? We'll cover how to evaluate them. Okay, so let's kick things off with the semantic revolution itself. This whole new world is powered by large language models, or LLMs. And when it comes to search, their power is usually channeled through three main techniques, which we're about to introduce. So, first up is dense retrieval. This is really the heart of semantic search. The big idea here is to turn your query and all your documents into numbers, vectors, and then just find the closest matches. It's like a find the nearest neighbor game, but for meaning. Then you've got re-ranking. Think of this as a quality control step. It takes a bunch of initial results and uses a more powerful model to resort them, putting the absolute best ones right at the top. And finally, there's RAG, Retrieval-Augmented Generation. This is where things get really cool, because it combines search with generation. It finds relevant info first, and then uses that info as a cheat sheet for an LLM to write a brand new, synthesized answer. Let's start with that foundational technique, dense retrieval. This is what really marks the shift from searching for specific words to searching for abstract concepts. And the whole thing is made possible by this core machine learning concept called embeddings. So, what on earth are embeddings? Well, at their core, they're just a way to turn text into numbers. They translate the complex, nuanced meaning of human language into a format that computers can actually work with mathematically, basically long lists of numbers called vectors. An embedding model reads a piece of text and spits out a vector that acts like a coordinate, placing that text in a specific spot within this giant, multidimensional meaning space. And this is the core intuition that makes it all work. Just imagine this huge space where every single piece of text, a word, a sentence, a whole document, is plotted as a single point. The real magic is that the model learns to place texts with similar meanings close to each other. So the vectors for king and queen would be right next to each other. The concepts of puppies and kittens would be clustered together. It's this simple geometric relationship that powers the whole idea of semantic search. So how does this work in a real system? Well, the pipeline usually has four main steps. First is chunking. You can't just embed a whole book, so you break down large documents into smaller, more manageable pieces. Second, you embed. Every single one of those chunks gets converted into a vector. And when you type in a search query, that gets turned into a vector too, using the exact same model. Third, you store. All those document vectors in a special kind of database, a vector database that's built for super fast similarity searches. And finally, you retrieve. The system zips through that database to find the document vectors that are mathematically closest to your query vector, and those are your results. Let's look at a quick example to see how powerful this is. Say we're searching an article about the movie Interstellar, and we ask, how precise was the science? A classic keyword search just grabs onto the word science and gives us a pretty generic result. But look at the dense retrieval result. It understood our intent. It knew we were asking about accuracy, and it found the sentence talking about praise from astronomers for its scientific accuracy. I mean, that's a perfect answer, and it doesn't even have the words precise or how in it. Of course, building these systems isn't always straightforward. There are a few practical things you really have to think about. First is your chunking strategy. How you decide to split up your documents. By sentence, by paragraph, with some overlap, that's a huge design choice that can really affect your results. Second, you have to deal with irrelevant results. A vector search will always find the closest match, even if that match is still really far away and not relevant at all. So you need to set a threshold to filter out the junk. And finally, there's domain specificity. A model that's great at understanding Wikipedia might be terrible with legal contracts or medical research. You often need to fine-tune these models on your specific type of data to get them to work well. All right, let's move on to our next technique. So dense retrieval is awesome, but what if you want to make your search even smarter? Or maybe you already have a search system and you just want to improve it. Well, that's where re-ranking comes into play.
A re-ranker is a specialist model. Its job isn't to do the initial search. Its job is to take an existing list of results and just reorder them. So you might get the top 100 results from a faster search method, and then you pass them to the re-ranker. It then uses a more powerful and, more computationally expensive analysis to figure out the true order of relevance with much higher precision.
This creates a really effective two-stage pipeline. The first stage is all about speed. You want to cast a wide net and quickly pull in a bunch of documents that might be relevant. The second stage is all about precision. Here you use a more powerful model, usually what's called a cross-encoder. Now, what's cool about a cross-encoder is that it looks at the query and each document at the same time, which lets it make a much more nuanced judgment about how relevant they are to each other. This two-step process gives you the best of both worlds, speed and accuracy. And now we come to what is arguably the most exciting application of all this, where search and generative AI come together. Let's talk about Retrieval-Augmented Generation, or RAG. So, you've probably heard about this major problem with large language models. They have a tendency to hallucinate. Basically, they just make stuff up. They'll generate answers that sound totally plausible, but are factually wrong. And that's because they're built to predict the next word, not to stick to the facts. So the big question is, how do we force these models to be grounded in reality? Well, the leading answer to that problem is RAG. RAG is a really clever two-step process. First, it uses a retrieval system, like the dense retrieval we just talked about, to go out and find factual documents that are relevant to your question. Then, it takes those documents, bundles them up with your original question, and hands them over to a large language model. It's essentially telling the model, hey, here's the answer. Just use these facts I'm giving you to write a nice, coherent response. I love this analogy. A regular LLM is like a student taking a closed book test. It's relying completely on what it memorized during its training. But a RAG system, that's like giving the model an open book test. You're providing the source material right there on the spot. This massively reduces the chance of it making things up and ensures that the answer it gives is grounded in real, verifiable information. The RAG pipeline is super logical. It all starts with the user's query. Then, in the retrieve step, a search system goes and finds the most relevant text passages from a knowledge base. Next comes the augment step. Here, the system creates a new, super detailed prompt by combining your original question with all that retrieved text. And finally, the generate step. That big augmented prompt gets sent to an LLM, which is instructed to write an answer using only the context it's been given, often with citations pointing back to the sources. Okay, so we have these incredible, powerful search systems. But how do we actually know if one is better than another? This brings us to the really critical topic of evaluation. Just look at this scenario. You've got two systems, System 1 and System 2, both found one relevant document in the top 3. So if you're just counting right versus wrong, it's a tie. But we all know System 1 is better, right? Because it put the correct answer right at the top, position number 1, where you're actually going to see it. We need a way to measure performance that rewards that. And the metric that does exactly that is called mean average precision, or MAP. The basic idea behind MAP is that it doesn't just count correct answers, it heavily weights the ones that appear higher up in the list. It calculates precision at every single relevant spot in the ranking and then averages those scores. This means it inherently rewards systems that get the good stuff to the top. It's a great way to boil down performance into a single number so you can compare different systems head to head. Now, evaluating RAG systems gets even trickier. We're not just looking at a ranked list anymore. We have to judge the quality of a whole paragraph of generated text. This means you have to look at several things. Faithfulness. Does the answer actually stick to the source documents? Answer relevance. Does it really answer the user's question? Fluency. Is it well written? And citation precision. Do the sources it cites actually back up what it's saying? This often requires human judgment. But a really cool area of research right now is actually using other powerful LLMs to automate scoring these more qualitative things.
All right, we have covered a ton of ground on modern search. Let's take a moment to step back and just quickly summarize the biggest takeaways from this whole discussion.
When you boil it all down, there are really three main ways LLMs are supercharging search today. First, dense retrieval lets us search for meaning, not just keywords, by using embeddings. Second, re-ranking acts as a refinement layer, taking a good set of results and making them great by improving the order. And third, RAG combines that powerful search with generation to give us factual, synthesized answers that are actually grounded in real data, which is a huge step in fighting hallucinations. You know, these technologies are a massive leap forward. They're helping us tackle one of the biggest problems in AI, the factuality problem. But with technology, as soon as you solve one challenge, the next one comes into view. So I'll leave you with a final question to think about. Now that we have these incredible tools to make AI more factual and more grounded in reality, what's next? What's the next big challenge for us to solve in language technology?